Everybody. This discussion is going to be on lasers, and we're going to review lasers in general today. Lasers, as you know, have many functions, and you probably have seen their use in other areas. As a dental hygienist, you may be expected to use a laser in private practice, and in Virginia, that is part of our scope of practice. So it's important for you to have a foundation on the laser so that you're able to make sound judgment on how to incorporate the laser into your clinical setting for the best clinical outcome for your patient. So Einstein said it best. The world we live in today has problems that cannot be solved with the same critical thinking we thought when we created them. We are not using lasers the way that they were initially created. The use of lasers have shown a variety of advantages to different uses, but by attending today's lecture, and from what you've read already, you're going to know what the professional responsibility is to yourself as well as the community to recognize when to use the dental laser. You'll also be able to use the laser in a safe manner and practice the use in our dental hygiene clinic. Our clinic has protocols and guidelines, not suggestions, but guidelines that you need to follow for safe practices. If you knew that sticking a laser in your eye would cause blindness, would you want your partner to practice unsafely on you? So please follow safe practices. That's what you're going to learn today, and as well as in lab. And by understanding the use and limitations of lasers, you as a healthcare provider can play a vital role in providing comprehensive care to your patients. So we've got some objectives that we're going to go over, and by the end of this lecture, you should be able to define the terms of what the laser is, discuss the difference between the average power and peak power, describe the 4 major categories of dental lasers in use today, and explain the role of the laser fluorescence in caries diagnosis and management, as well as display a professional commitment to use the safety practices of all laser types. You're also going to know the advantages and disadvantages of these topics in detail. So we're going to go over the history and the laser tissue interaction, laser beam delivery system, and classification of lasers, as well as the safety. We're going to look at the uses of the lasers in dentistry, some of the advantages and disadvantages. What's the armamentarium? How do you set things up? And the technique for clinical laser use as well. So let's start out with the fundamentals of lasers. Each of the topics are going to have subheadings, and with the fundamentals, I will review in detail of the light, the definition of what a laser is, and we'll go into simulated emissions and the design mode of operation, as well as the laser parameters. So let's look at the history of how light was used. The ancient Greeks called light heliotherapy. Heliotherapy was used to treat tuberculosis in the 1800s. Ancient India used sunlight to treat vitiligo, or the loss of skin color, and ancient Egyptians used the light to treat leukemia, or the loss of skin color. Only in 1974, ultraviolet A was enabled. And remember that natural lights are the essential energy source. The light rays from the sun, which travel at about 300,000 kilometers per second and take about 8.5 minutes to arrive at the Earth. So what is a laser? The definition of a laser is brought to you by Wikipedia. The term laser is an acronym for light amplification, by simulated emission of radiation. So with the laser physics, you've got a laser that's based on the atomic energy level transmissions, but it's got a little bit of a twist with it. It's got spontaneous emission, and that's when the electron transitions on its own from higher to a lower energy. And the atom loses energy in the form of a photon. Now, a photon should sound familiar to you, because you learned this in radiology. In fact, it almost looks like the exact same picture that you had. How does the simulated emission work in a laser, though? Let's look at the first target image labeled spontaneous emission, the one on the left. The electron is initially on the outer shell and becomes excited to see the second target image. And this electron shoots off and leaves the rest of the electrons to hang with more popular and exciting target signs. Then in spontaneous emission, the electron moves to the inner shell. When this happens, the spontaneous emission electron joins simultaneously absorption on the inner circle until it becomes excited to see the third target sign, and that's called stimulated emissions. This electron joins at the outer shell and moves inward to the inner shell, but is later pushed out from the inner circle. Now, luckily, you're not going to have a test question on that. So what are some of the 5 keys to simulated emissions? This is in the third target sign, and this is stimulated emission. So you've got energy that is required initially to raise the electrons to a higher level, and both the energy and the direction of the incoming photon are not affected, and the emitted photon travels in exactly the same direction as the incoming photon. The emitted photon is exactly in phase with the incoming photon, and the incoming light is amplified because for every one input photon, there are 2 output photons. And I apologize for the typo there. The incoming light is amplified because for every 1 input photon, there are 2 output photons. What's a photon, you ask? Well, let's break it down even further. Energy that is lost from an atom is lost in the form of a photon. The photon is energy that makes up all forms of light. So the atom loses energy in the form of a photon. So let's talk about energy. The wavelength is how we measure the energy. A wavelength is measured crest to crest. The physical property determines the classification of the electromagnetic energy, and lasers are named by the characteristic wavelength and active medium. The distance a photon travels through a complete oscillation is measured from peak to peak in meters, such as micrometers or nanometers. Peak to peak. Here's an electromagnetic spectrum in reference to wavelength. And you've seen similar pictures before as well. But you can see the more red the visible light is, the further the wavelength peak is. So on the right of the picture, you've got that low and slow energy spectrum. In the middle is visible light, and on the left is where the X-rays and gamma rays lie. Do you notice the difference between the peaks? The closer they are together, the more energy is being produced. Remember that kVp, kilovoltage peak? It's the same philosophy with that. So we use in dentistry, for dental hygiene use, we use a diode laser, which is 8-10 nanometers, and that falls between the red and the ND YAG laser as well. So lasers have 3 distinct characteristics that distinguish it from ordinary light. The monochromatic, okay, that's the light is all one wavelength and therefore all the photons are the same color. Or you've got collimated because the laser lights travel in a straight line versus the multi-directional. And it's coherent, which means that all light waves move in a phase together in both time as well as space. So you have monochromatic, collimator, and coherent. Let's look at the different laser types. And there are 4 types of lasers here. You've got a solid state laser, which is an active medium suspended in a transparent crystal. And the host material is grown in and doped with atoms that will create the desired wavelength. You have gas lasers, which have hollow tubes filled with the appropriate gas or mixture of gases. There are liquid dye lasers that have dye dissolved in methanol or water solvents, and it's not used in dentistry. And then you've got the diode laser, which is what we use in dental hygiene, and that's a semiconductor, and crystals are pumped electronically and, again, used in dentistry. So the liquid dye laser is not used in dental dental treatment. We are using diode lasers, which have a semiconductor. So the laser energy leaves the fiber and it's no longer collimator. Still sounds kind of like radiology class, doesn't it? Because once that energy leaves, it wants to diverge. And the divergent, the light travels in a straight line until it's absorbed, reflected, or refracted. So this image shows the reflected version of the laser light. You always want to use the lowest power setting to achieve the desired results in a reasonable amount of time. What if we tried a little bit more than needed? Well, there could be possible tissue damage that could occur. So if you understand the physics of your radiology course, then this will make more sense to you. Now, what's some of the terminology with the use as well as the conversions? Again, this isn't something that you're going to be tested on, but it's trying to give you a bigger picture of what we are doing with our patients and what power the machine actually has. So when you have pulses per second, which is the number of firing cycles per second, boop, 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 like that, it is measured in hertz. Even your ultrasonic scalars are measured in kilohertz. You've got a 30 kilohertz magno-restrictive ultrasonic unit. So the terminology is really the same. So that's a hertz. Now a joule is a unit of energy that's needed to do the work. Then you've got your watts, which is a unit of power, which is the rate of doing the work. So for conversions, this means 1 watt equals 1 joule for 1 second. Okay, so if you really want to get into the conversion, here's how it's broken down on the right-hand side. That's too much math for me. So the laser operates in 3 different modes. You've got a continuous mode, a graded pulse or chopped pulse mode, or a free-running pulse mode. So a continuous wave mode is a laser that is on the entire time, okay? Zzz, continuous mode, just what it sounds like. The graded pulse or chopped pulse mode means that the laser is blocked, chopping the laser beam in varying speeds. Then you've got the free running pulse mode, which means that it isn't on constantly, but emits photons in powerful bursts of energy. So that is also your intermittent mode. And that's what we use when we use this in dental hygiene. We use a non-initiated tip in a intermittent or pulse mode, all right? And those are the things that we're documenting in the chart after we do laser therapy for our patient. We need to discuss the wattage and the mode of operation and all those parameters. So each of the modes have an important characteristic when the laser interacts with tissue.